Hi guys, in today's video I would like to show you this 3D scanner that I made that consists of this time of flight sensor and two analog servos and an STM board. So it's quite simple in these terms, and as you can see this time of flight sensor is positioned directly above this axis and also along this axis, so it is capable of changing its yaw angle, this angle, and also the pitch angle. So this 3D scanner has limited range of motion, so its pitch goes from 0 degrees, which is horizontal, up to 90 degrees up, and its yaw range of motion goes from 0 degrees up to 180 degrees. So that's its range of motion. So this was on the first scan. So I've made this application in Java that uses 3D chart, JZ2i3D, and you can select your virtual COM port, which is my ST board, select the maximum pitch and hit the scan. So as you can see in this console on bottom left, there are values and positions which were sent to my ST board, and as the scan is in progress, you need to click on this preview button to actually see what was scanned. So let me just skip this video a little. So as you can see the progress of the scan, and in the end you can check what was actually scanned. So over here, here's the lamp, here's the gap between the lamp and the speaker, here's the speaker, the bottle, and this furniture. So let me just check the correct perspective. So if we will compare it with this, so here's the furniture, here's a bottle, a speaker and a lamp, and the gap between the lamp and the speaker. So here it is, here's the speaker, a bottle, furniture, and the lamp. So, and here's the gap between those two. So as you can see, this is the 3D scan, the first one. And this was the second scan that I made. This was without the bottle. So there was only that furniture, that shelf on the left, a speaker and a lamp. So this is what the scan actually looked like. So here you can see that lamp, the gap between the speaker and the lamp, and these two faces of a speaker and of that furniture, of that shelf. Yeah. So this is it. When it comes to hardware of this project, I've used this STM board as a virtual COM port that uses this USB peripheral, and for that purpose I have resoldered this 1.5K resistor R10 to PB3, and this way I can enable that USB communication at will. And that time of flight sensor that I've used is this VL53L0X sensor from ST Microelectronics, and there are plenty of different variants. There's also L1X that has range of 4 meters, but this L0X that I've used has range up to 2 meters. So you would probably need to use a different library for this one. And as you can see, some of these has this linear regulator. So therefore I've connected this module to 5 volts. And this regulator regulates it down to 3.3 volts that this time of flight sensor actually needs. So when you buy a different module, they may have or may not have these 3.3 volt regulators. So it depends what you buy, and you need to double check it, because 5 volts would cause a damage to this sensor. And when it comes to 3D models, I've modeled this base in FreeCAD. So here's a hole for a servo, and here's a place for this STM board, as well as this cutout for the USB cable, and this is a hole for the debug cables for these debug peripherals. So it's easy to connect those pins. This is the horn for the servo, which has a hole at the bottom. So this is just to mount this top mount of the servo. So I had to print only these 3 parts, and I was able to assemble it. So this part, this horn, and this side mount are technically free to mount onto each other. I had to glue only this one and this one, but you can tightly fit in a servo into this side mount, and also you can just push inside a servo without having to glue it in. It is just tight. So this worked out well for me. So that's all for this hardware and this mechanical design. So when it comes to this STM32 project, this frequency I have set up to maximum possible frequencies, and when it comes to these peripherals, I've used this USB peripheral as a virtual COM port, this USB enable pin to enable the communication, and also this I2C2 for this time of flight sensor, and also this time of flight enable pin, which is called as a X-shot pin on this time of flight sensor. So, but basically you can turn on and off this time of flight sensor. And this timer 2 that I've used, it is used for these PWM channels for servos, and this timer 3 is set up to 1 second period. That enables me to count how many seconds I have passed since the last command from a computer via virtual COM port, and after 5 seconds of not receiving any command whatsoever, this program sets these servos to this home position, which is 0 pitch and 90 degrees yaw. So that's only for that purpose. It's quite simple. So as you can see, I just initialize these timers, set the pitch and the yaw to its default positions, and then I try to initialize this time of flight sensor. Sometimes you may have an issue during the power up and initialization of this I2C. So when you have this SR2 register at value of 2, it means it is busy for some reason, but you know that you are trying to just initialize this peripheral, so you just need to deinitialize it and initialize it again, and then you can try to initialize this time of flight sensor. Then I just wait 2 seconds, and after everything is initialized, then I can enable USB communication. So after power up, the USB communication initializes after 2 seconds. And here's some simple measurement handler, let's say. Over here, here I've made these definitions for the pitch mean and pitch max, and these values are technically for the PWM value for servos. So since these servos are analog, you need to calibrate them and you need to find out what its 0 and 90-degree position is, and also this yaw 0 position and 180-degree position is. So here are some simple variables, pitch and yaw, that measure flag for this measurement handler, and this homing counter. So when you receive a command to measure, this homing counter is set to 0, but in this interrupt, let me go here. In this interrupt source file, it homes those servos if there were 5 or more seconds of not receiving any command whatsoever. So that's basically that purpose of this timer. And everywhere I just include this my library in every source file, as you can see, as simple as that. And this my library consists of only of these three functions: set pitch, set yaw, and measure distance at this position. So when you try to set the first position, which is 0 pitch and 0 yaw, it waits 2 seconds. So you have those servers have time to get there from any position, and also you have those 2 seconds to move away before the measurement actually starts. And if the pitch and yaw is different, then the delay is quite short because those servos need only to move only by 1 degree at a time. So that's quite simple. And also over here I just included this my library, and over here I just have this format of received message. Let's say this is 89 degrees of pitch and 2 degrees of yaw. So this is what it looks like. And over here I just parse those values and set the measure flag to 1. And that's basically it. And it's as simple as that. And this time of flight library was made by Larry Bank, but it was made for Arduino platform. So I just modified this slightly to use these STM functions, such as HAL I2C functions, and this HAL delay. So, but that's all about it. So this credit for this library goes to that author, to Larry Bank. So it's not that complicated. This ST board just receives some commands, measures that distance, and sends back the result. So it's as simple as that. So let's move on to JavaFX application. So I also made this 3D scanner application. So this one is made in Java 15 and using JavaFX 15 framework. And I'm using this latest Java and JavaFX because this JZY3D library, it technically uses the latest JavaFX. Therefore, I had to build it in the latest Java. So let's say in this application you can set up a maximum pitch. It goes from 0 degrees up to 1 degree. Here you can pick up your 3D scanner, and I can connect to it. And when I hit the scan, as you remember, the first position 0, 0 takes 2 seconds, so you have time to move away from that sensor, and that sensor, those servos have time to get to that position in that 2-second period. So as you can see, now it just moves quite slow, but it is good speed for the measurement. And as you can see, nothing is rendered, only after I click this preview. So this is what was actually scanned. So this way you can render this 3D chart as you want at will. And this scan will be fully rendered only after the scan was done. So when it hits 100%, this is gonna wait 5 seconds and goes to home position. So this was that timeout of that timer 3 of this STM board that I was explaining a few minutes ago. So this thing, this scan is finished. But since I was moving this with my hand, you can see that distortion. So this 3D scanner is supposed to be stationary. And as you can see, this window, this stage is quite squared, and I need to keep it squared all the time. So therefore I can avoid this distortion. So this way you can scan anything you want. You can just set up the maximum pitch range and hit the scan. And you can even cancel that scan. When it scans, you can just hit the disconnect, and it works as a cancel of that scan. So this is what was scanned, and that's all. And to implement this JZY3D, you need to use this Maven. It is a build script, and I made an entire tutorial 1 year ago how to make it work from scratch. So if you want to make it on your own, just watch this tutorial. It is for JDK 13, so for Java 13 and for the JavaFX 13. So it's the same, but this project uses the latest Java. That's it. And I only used a simple pane, some image view into which that 3D chart is rendered. So that 3D chart is a rendered image into an image view, and there's a listener on that image view to be able to rotate that chart. And that's as simple as that. As you can see, I have few listeners for the width property, and I always keep the size of the width the same as well as the height, so that way I keep the stage squared. Here's that render button. I've made this simple progress bar, and as you can see, it is quite simple. This timeline updates that progress bar until the measurement is fully updated at 100%. So this timeline runs forever. but only updates that chart until the scan is at 100%. Here is that scan button. It resets the value, starts a new thread, and runs that progress bar. So it is quite simple, just a few lines. Here I reset the scan, reset values. Here's the render routine to generate a new chart. Here's actual that 3D chart function that generates that chart, and here I just try to get those data points, and here I draw them. It is a part of this 3D chart function. And this scanner is technically spherical because there's only a single point, and I change the pitch and the yaw. So, and over here I have this thread that decides whether to send a request for the new position, or down here to increment that pitch and the yaw. So it is an independent loop, and I had to run it on a separate thread. And so the JavaFX application is one thread. This is another thread that manages that communication, and there's a separate thread that is this serial comport. And over here, here's my message handler. When you look at this message handler function, maybe this part is quite interesting, because it says that sometimes you can receive one message and sometimes you can receive even more, in this case 2 messages. So normally you receive only one message at a time, but when you cancel the measurement, there will be the last message in the buffer unreceived or received but unprocessed. Therefore, only in that case, when you stop the scan and start it again, that first message you will receive, there will be actually 2 in the buffer. Therefore, the second one is the latest, but every other message you will receive, there will be only 1 message again. Only when you restart the scan, there will be 2 messages. So that's all. So when I receive a message, it switches this flag to measure flag, so we can measure it again. And over here I have all the objects and values. So you can learn about it. Everything is shared on my GitHub. Also, this author of that time of flight library is credited over here. So that's all for today's video. Just reverse engineer my code, change it, and you can also technically change that time of flight sensor for that L1 model, which has 4-meter range, or you can replace this with an ultrasonic sensor. It's up to you. So this is quite a simple project. So see you next time. Bye.